This conference will now be recorded.
Hello everyone. We'll start with this problem. Though this problem we have already discussed, but just little correction I want to make. The question is asking that in basic medium H2O2 exhibits which of the following reactions. So it is not specifically talking about whether oxidation or reduction reaction. It is simply asking that in basic medium which of these reactions are possible. Now the first reaction here, from 2 plus to 4 plus, oxidation state is changed for manganese, so it is basically oxidation reaction. And for the second reaction, iodine from 0 elemental state, it is gaining electrons, so this is basically reduction. And the last one, from plus 2 of Pb, this is also plus 2. So with respect to Pb, there is actually no change in oxidation state, but if you consider sulfur, here it is minus 2, but in sulfate ion, the oxidation state is plus 6. So with respect to sulfur, this is obviously oxidation. So the first one is oxidation, then reduction, then oxidation. Now in the last class, by mistake, I have said that iodine is, there is a reverse reactions I have considered, but basically the actual question I have checked again. In this case, it is basically I2 to I minus conversion. So this question actually came in JE. So that is the correction I want to do here. So the first one is oxidation, then reduction, and then again we have oxidation in the third reaction. Choose the most appropriate answer. Now in the last class, I also have selected, actually the answer is correct. It is basically the 4. That is only A and B, these two reactions are possible, but the last one is not possible. Okay, but as I have reversed this reaction in the last class during the discussion of this question, so that is the correction I want to make here. So see what are the actual detail if we see for these reactions, because here it is simply focused on just one species, but what is the full reaction if we see. So when it is Mn2 plus to Mn4 plus conversion, you can take this salt, which is basically Mn2 plus. So MnSO4, that is converted to MnO4. Here it is plus 4 and here it is plus 2. That means from plus 2 to plus 4, that is the conversion. So this is oxidation. Now the next one is iodine is converted to I minus. Now this reaction is possible in basic medium, which is clear from this equation, HO minus. And the last one is again oxidation, and that is with respect to sulfur, minus 2 to plus 6. And see here we do not have any basic medium, so this reaction is not occurring in basic medium, it is neutral. So that is why correct option is only the last one, that is the first one and the second one, not C, only A and B. So this is the problem. Next we'll discuss another problem, and after discussing problem we will switch to one more chemical properties of H2O2 is left. We will finish that, and then we will start uses of H2O2. That is also very important. And once we are complete with H2O2, next topic will be hydrogen as a fuel and hydrogen economy. So look at this question now. The oxidation state of manganese in the product obtained in a reaction of potassium permanganate and hydrogen peroxide. So potassium permanganate is KMnO4 and hydrogen peroxide is H2O2. So KMnO4, here we have oxidation state plus 7, and this is very good oxidizing agent, actually very strong oxidizing agent. Now it is asking that the reaction between these KMnO4 and H2O2 in which medium, that is very important. It is in basic medium, because if it is mentioned as acidic medium, now KMnO4 it is changed to plus 2 state. Okay, but if it is basic medium, now it is changed to plus 4 state, and that is mainly MnO2 compound. So remember this, when it is acidic medium, the conversion is plus 7 to plus 2, but when it is basic medium, this is fixed. H2O2 is fixed. But whether you have taken acidic or basic medium, depending on that, oxidation change is different. 7 to 2, here 5 electron difference, and 7 to 4 in basic medium, it is 3 electron difference. And remember in redox chapter also, this the same mention, I have already mentioned it, and also very important information that KMnO4 its oxidizing property is maximum when it is in acidic medium, not in basic medium. And that is also clear here, because +7 to +2 it is 5 electron change, but when it is in basic medium it is basically 3 electron change. So 5 electron gain versus 3 electron gain, obviously 5 electron gain it is more oxidizing capacity. But in our question it is asking in basic medium, so the answer is from +7 to +4. This is the change in oxidation state. So it is a fill in the gap type of question. The oxidation state of manganese in the product which is obtained when there is reaction between KMnO4 and H2O2 and it is in basic medium. So the oxidation state is basically +4. So the answer is 4. Fine. Next question. On reaction with stronger oxidizing agent like KiO4, potassium iodate, KiO4, hydrogen peroxide oxidizes with the evolution of O2. The oxidation number of iodine in KiO4, which is basically the starting material, changes to which oxidation state? That means here we have this IO4 minus ion. Simply remove the potassium. What you will be left with? You will be left with IO4 minus. Now this IO4 minus, now it is oxidizing agent. It is already mentioned, it is strong oxidizing agent. So there will be gain of electron. Now look at this species, that is this anion. What is the oxidation state of iodine? It is basically +7, because we have -1 overall charge. There are total 4 oxygen. For each oxygen it is -2. So total negative charge is -8. So total positive charge must be +7, so that overall charge is -1. Now +7, that is the maximum oxidation state possible for it, and that is why it is very strong oxidizing agent. Now it is eager to accept some electron, and thus it will show oxidizing property. So what is the actual reaction going on? This is the actual reaction going. See, KiO4 plus H2O2, it is converted to KiO3, H2 and O2. And also if you are finding any difficulty to writing the equation, this information will help you that with the evolution of O2. That means here O2 must be present in the right hand side, evolution. And here the species is KiO3, where the ion involved is IO3 minus. So when it is IO4 minus, the oxidation state is +7, and when it is IO3 minus, it is basically +5, because now you have 3 oxygen. So total negative charge is -6. Overall negative charge -1. That means positive charge must be +5. So this is the way how we calculate oxidation state. Details we have seen in the redox chapter. So this question you can say it is a combination of the 2 chapters also. So here the answer is from +7, now it is changes to +5. Next question. H2O2 oxidizes FeCN64 minus. So when it is FeCN64 minus, you can easily calculate the oxidation state of iron. It is +2, because per Cn it is -1 charge. So total negative charge 6 minus. Overall outside the bracket you have 4 negative charge. So the positive charge over Fe must be +2. And it is changed to FeCN63 minus. So now the oxidation state is +3. So H2O2 is oxidizing from Fe2 plus, now we are getting Fe3 plus. And this is occurring in acidic medium, but it reduces FeCN63 minus. Now this is the starting material, FeCN63 minus, and it is changed to Fe2. So now it is reduction from Fe3 plus to Fe2, but now it is in alkaline medium. So this is the information given. Now it is asking the other products form. Fine. So in the options 1, 2, 3, 4, we have so the first combination that you are seeing, that is H2O2, only H2O, H2O, then again H2O2. So this is for the acidic medium, because it is respectively. And the second combination, H2O hydroxide and H2O2, H2HO minus, and simply H2. That is in basic medium. Now remember, Obviously, if you can remember the equation, that is the reaction between H2O2 and this iron cyano complex, that is obviously fine. But the two general equations also I have mentioned during the discussion of chemical properties in the last class, where the byproducts are clearly mentioned. We will also see those equations. But first, see what are the actual reactions going. K4FeCN6. So the first reaction, it is in acidic medium, and the second one, it is in basic medium. So in the first case, Fe2 to Fe3 plus conversion, and this is basically oxidation. In the second case, it is reduction. Here it is Fe3 to Fe2 conversion. Simply remove these 3 potassium plus, what you will get? You will get 3 negative charge here, right? Which is, there is anions are mentioned in the question, but here the equations are written with potassium ion, that is the counter ion. Now look at the byproducts in the right hand side. In the first case, acidic medium, you have water. In the second case, you have H2O and O2. So acidic medium, only water. In the basic medium, it is water and O2. So second option is matching. But remember the two equations that I have already mentioned in the last class. That also will help you, irrespective of the fact that with which species H2O2 is actually reacting. Because these equations, as you can see, the first equation in basic medium, it is gain of electron by H2O2. So this is reduction. I mean reduction with respect to H2O2. So in this case, better I write, it is showing oxidizing property. So it is showing oxidizing property. And in the second case, it is donating electron, so it is showing reducing property. So when it is showing reducing property in acidic medium, byproducts O2, basic medium, water and O2. And when it is showing oxidation property, acidic medium, water and basic medium, hydroxide. Now in our case, in acidic, both are basically, sorry, let me change the color. So in our case, the first reaction, it is in acidic medium and it is basically oxidation. In the second case, it is basic medium and this is reduction. So acidic medium, oxidation, that means this one. And the second one is basic medium, reduction, that means this one. Now look at the byproducts, water, here also mentioned, and H2O2, that you can see. So in this way, view from the general equation also, we can choose the correct option, that is the second option. Right? One more chemical property of H2O2 is left after the most important chemical property. We just finished that, and that is oxidation property of H2O2 and reduction property of H2O2, that we have started in the last class and today we have completed. Now we have formation of CrO5 complex. So chromium with 5 oxygen. How this complex is formed? In an acidic solution of dichromate. Dichromate means Cr2O7, 2 negative charge, overall charge 2 negative. Treated with H2O2 in presence of some organic solvent like ether or amyl alcohol. Now if we do so, now a deep blue solution, ether and amyl alcohol, these are basically acting as solvent, organic solvent. A deep blue solution of chromium pentoxide, CrO5, or it is also called chromic peroxide, is obtained in the ethereal layer. So suppose we are doing the reaction, there is water as well as there is ether. Now ether and water, it will not mix. That is organic solvent, it will not mix with water. So you can separately visualize the ether part and the water part. So in the ether part only, there will be a specific color. So it means in ether part, the complex is soluble. Now you can call the complex here chromium pentoxide because there are total 5 oxygen. or you can call it chromic peroxide. Now, if you are calling it chromic peroxide, that means there must be some OO linkage. Otherwise, how you can call it chromic peroxide, right? One more important point is, what is the oxidation state of this compound? If you simply follow the how we calculate oxidation state. So there are 5 oxygen, and so total negative charge will be -10. Then chromium, is it having +10? No, that is not possible at all. Maximum oxidation state of chromium is +6. You cannot get more than that. So it means all the 5 oxygens, they are not of similar type. There are 2 different types of oxygen. So one oxygen, it is involved in peroxide, and there is another oxygen which is not involved in peroxide. So when it is peroxide oxygen, you cannot consider -2 charge. So that is why we are having some wrong oxidation state if we simply follow -2 for all the 5 oxygen. So look at this equation, K2Cr2O7, which is containing dichromate with potassium, you have to call it potassium dichromate. Then acidic medium and H2O2, we are getting chromium pentoxide or chromic peroxide. Now this is the molecule, how it looks actually. You can see here 2 different types of oxygens are present. So chromium double bond O. So for this oxygen it is obviously -2, but these two are peroxide linkage. Now if you just flip this chromium oxygen bond, there is -1 charge, -1 charge. So total negative charge here it is -2, -2. So 3 -2. That means total negative charge -6. So oxidation state of chromium is +6. So I'm writing here +6. So important point is, before reaction and after reaction, there is actually no change in oxidation state, because when it is chromium Cr2O7 2-, here also the oxidation state of chromium is +6. So you can easily calculate it. Suppose it is X, so it is 2X because 2 chromiums, and 7 oxygen. For each oxygen it is -2, and overall charge is -2. So here the value of X will be 14 - 2 divided by 2, which is +6. So before reaction, after reaction, there is no change in oxidation state with respect to chromium. That means it is not any redox reaction. That is, it is not that H2O2 is showing any reduction property, or that is not the case. So CrO5 is stable in ether or amyl alcohol part. So that is why we have taken this while doing the reaction. Oxidation state of chromium in both K2Cr2O7 as well as CrO5, it is same. There is no change in oxidation state. So remember, you can get question related to this complex. Specific information are there. It is having very interesting structure. It is also called having a Z butterfly type of structure because of this shape. And there are 2 different types of oxygen. Peroxide linkage is there, normal oxide is also there. So be careful when you are calculating the oxidation state of the chromium, and there is no change in oxidation state, so there is no reduction or oxidation going on. Fine. So this is the last reaction, chemical properties of hydrogen peroxide. Next, application of H2O2. Now applications are very versatile because of its different interesting chemical properties. So how it is versatile? Industrial use of H2O2 is as bleaching agent. Remember, in chemical properties we have seen it has some bleaching action, and that is because of the nascent oxygen which we represent like this, and it can bleach delicate materials like silk, wool, paper pulp, straw, oils, fats. In daily life we can also use it even as hair bleach and mild disinfectant. Also as an antiseptic, it is sold in the market in the name of perhydrol, which is 30% H2O2 solution. You know, we have discussed how to express its concentration. There are 2 methods, mass percentage and volume. By volume also we can express its concentration. So it is 30% H2O2, it is perhydrol, which is basically the antiseptic. It is also used in the synthesis of hydroquinone. So hydroquinone is this molecule. So it can be obtained from, no, I'm not drawing phenol because there are two H groups. So in presence of H2O2, it can oxidize this molecule to hydroquinone. Okay, so here aromaticity is lost. Then tartaric acid, that can also be produced from malic acid. So in malic acid there is CC double bond and there is CO2H. This is C structure, and when it is treated with H2O2, this CC double bond, there will be dihydroxylation. So two H groups will be inserted here, and as a result we get tartaric acid. So in this way it can be used for the preparation of hydroquinone, tartaric acid, certain food products, and even pharmaceuticals. Example, cephalosporin. Used in water treatment to oxidize pollutant because it has oxidizing property, and also as bleach in textile paper and hair care industry. Sorry, this is actually repetition. So just focused on this part, to oxidize pollutant. It is used in the manufacture of sodium perborate, which is having some other applications. So these compounds are important, sodium perborate and sodium percarbonate. Now, why these two compounds are important? Because they are having some cleansing properties and also bleaching actions. Now, what is the structure of this molecule? Sodium perborate. So it is basically Na2, B2, O4, total 4 oxygen atoms, and how many HO? Total 4. So this is the formula of this. Sodium perborate. Why perborate? Because you have this type of peroxide linkage here, and there is negative charge over boron because it has total 4 bonds, and these two negative charge, they are balanced by 2 sodium plus ion. And the second structure, sodium percarbonate. Now it's to some extent peculiar to look at this compound because there is not a fixed structure. Actually, what happens, if you focus on this part, it is basically carbonate ion, CO3 2 negative, and with 2 sodium it is basically Na2CO3. So you have 2 Na2CO3 together along with 3H2O2. So sodium percarbonate, it is represented like this, and that is all these cations, anions, and this neutral molecule, they remain together associated, and that is called sodium percarbonate. So these two compounds can, H2O2 can be used for the preparation of these two compounds. Some more uses we will see. It is used for restoring the color of lead painting. So lead painting, suppose in painting if lead is used, that is PB compounds are used, which has blackened because of action of H2S present in the air on lead paints. So if the painting is very old, for long time, if it is, that is in presence of air, whatever amount of H2S is present in air, though it is very low, but still for long time, if it is coming in presence of this hydrogen sulfide present in air, then this PB can react with this H2S and it can produce PBS. Now PBS, it is basically black color. So if we want to restore the original color of this painting, what we can do, we have to destroy this PBS. Now H2O2 can do so, it can oxidize this black colored lead sulfide to white colored lead sulfide. Now with respect to PB, there is no change in oxidation state. It is 2 plus here, also here. But with respect to sulfur, it is obviously oxidation from -2 in PbS to +6 in PbSO4. So PbSO4, it is white color compound. So that is why we can, there is this black stain that will be removed. So this is application of H2O. Next important application in rocket fuel. Now it is not used directly in the rocket fuel. How it is used? 93% H2O2 solution is used as an oxidant for rocket fuel. So the actual fuel, it is not H2O2, but what is the reaction here occurring? Hydrogen is basically reacting with H2O2. You can also write it as N2H4. So it oxidizes hydrogen to nitrogen gas. So this is nitrogen gas. And also water is produced and a huge amount of heat is produced. So this is actually the important point. With generation of lots of heat and this heat turns the water that is produced as byproduct into steam. So this steam is required for propelling the rocket. So in this way, it can which the engine can eject at a very high speed. That is, the steam can be ejected by the engine at a very high speed through a rocket nozzle. So here this hydrazine, it is oxidized by H2O2 and water produced, N2 gas produced, heat produced. This heat is converting water to steam, and that is actually the engine is using for ejection at a very high speed through rocket nozzle. It is used in the laboratory for detection of presence of these elements: chromium, titanium, vanadium, transition metals. They are salts actually, with which, now how we detect it? Because it can yield peroxide of characteristic color. So when you are treating this chromium, titanium or vanadium, if you are treating some salts of this compound with H2O2, peroxide of these metals can be produced, and these peroxide of metals, there is having some different characteristic color. So from this characteristic color, you will be able to understand which metal is actually present. So this is also another application. So look at this problem. It is related to this rocket fuel, this point. 90% H2O2 is used as an oxidant for rocket fuel with hydrogen. So simply observe this equation. It is asking it is true statement or false statement. This is basically true statement, though it is 93-90, more or less same. So this is true. Fine. Uses of H2O2 is complete. Next, related to this. So in this question, the 4 statements that you are seeing, it is basically miscellaneous. See, the first one is it is decomposition of hydrogen peroxide. The second question is completely, it is not actually in this chapter. It is actually mixed, as if by mixing different chapters this question is made. Then the third statement, it is related to preparation method of H2O2 that we have finished, not in this class, in previous class. And the last statement, hydrogen peroxide used in the manufacture of sodium perborates, which we have just seen 2 slides before, isn't it? So it is asking among these, you have to find the correct statements. It may be the first 3 are correct, AC correct, all of them are correct, or ACD correct. Now decomposition of H2O, that we have used, we have seen several times. When it is decomposed, it produces water and oxygen. So it gives oxygen. This is basically true. Next statement is saying that like H2O2, compounds such as potassium chlorate, lead nitrate, sodium nitrate, when heated, liberated dioxygen. So look at the first statement. Here, when it is decomposed, we are getting oxygen gas. Is it also true for these 3 compounds? So for that, we have to see the decomposition reaction. So KClO3, actually by heating KClO3, O2 can be manufactured, O2 can be produced. So this is important preparation method for O2 itself. So KClO3, in presence of MnO2 catalyst and heat, it is producing oxygen gas. When it is lead nitrate, then also after decomposition, we are getting O2 gas. From NaNO3 also we are getting O2 gas. So these compounds, it is for the chapter of S block, you can get this knowledge, that is what will be the behavior of these compounds. And S block I am saying for sodium nitrate or KClO3, that is a compound of potassium, or that is P block also you can consider, where we have oxygen group 16, how we can prepare oxygen, that chapter may also. So it is basically S block or P block related chapters, fine. So this is true. Come to the third statement, 2-ethyl anthraquinone. So 2-ethyl anthraquinone is useful for the industrial preparation of hydrogen peroxide. So this type of molecule we have used. If I'm saying it is anthracene, basically all these three rings benzene ring, but as it is anthraquinone, these 9 and 10 positions, there will be C double bond O. And this position, this is 1, this is 2, at 2 position there is ethyl group. So this compound, if it is treated with oxygen molecule, that is, it is useful for the industrial preparation of hydrogen peroxide. So it can be used, that we have seen in the preparation part of H2O2. Okay. And then the last one, hydrogen peroxide is used for the manufacture of sodium perborate. So sodium perborate, we have simply mentioned in the uses of O2, sorry, in the uses discussion of H2O2, that it is used for the manufacture of sodium perborate, but actual reactions, if you see, it is basically this one, H3BO3, NaOH, H2O2. So this is the source of boron. It is used, that means this statement is also true. We are getting sodium perborate. This is the correct equation. So here all the statements are basically correct. Fine. So none of them are wrong. Next is hydrogen as a fuel. Comparison of energy, if we do, which is released in the combustion of different types of fuels. So here we will see a table where different types of fuels will be there. There is some conventional fuels, for example LPG, liquid petroleum gas, or octane. So we will take those and we will also keep in the column H2, so that we can compare that which fuel is more efficient. Now this energy released during combustion of these fuels, this energy released we will see in three formats. One is in terms of mole, that is when 1 mole of this fuel undergoing combustion, what is the amount of energy released. The unit will be kilojoule per mole. Then it will be also in terms of mass. So suppose per gram, what is the amount of energy released? Mostly it is gram, it may be kg also. And in terms of volume, volume is liter, mostly taken. So what is the, suppose I'm saying 1 liter is undergoing combustion. Then what is the amount in, that is what is the amount of energy per liter of the fuel. So all these three, in terms of all these three, we will see the energy released. Energy released, sorry, is combustion. In kilojoule state, that means kilojoule, it may be kilojoule per mole, kilojoule per gram, or it may be kilojoule per liter. Now in the second column we have taken H2 in gaseous state. Then the next column, it is also H2 but in liquid state. Then we have LPG, liquid petroleum gas. The next fuel we have taken methane gas, and the last one is octane. It is in liquid state. Fine. Now if we look at the per mole value, these two are close to each other. So whether it is H2 gaseous state or it is liquid state, the values are not highly different. So per mole 286 and 285. Then for liquid petroleum gas, it is 000. For methane 880, and then it is 5000 something. Now when if you consider the per gram, now these two values are high compared to the other three fuels that we have taken. And when it is per liter, now when H2 gas per liter, there is actually very small mass involved, because it is normal state, it is in gaseous state, right? But if you consider liquid, now per liter, obviously the mass is very high. So that is why energy released, that will also be high. And see, methane 35, and these two, it is around 25,000 or 34,000. But we will mainly focus on these values per gram, not per mole or per liter. So when we try to predict fuel efficiency, mostly we focus on what is the energy released per unit mass, that is per unit gram. If you consider gram, then obviously these two values are far high compared to these three. So 50, 53, 47 more or less same, and 143, 143, it is almost 3 times high compared to these three, right? So that means it is more efficient. So H2 can release more energy on a mass for mass basis, okay, which is almost 3 times than petrol. So octane is also called sometimes petrol, also 3 times compared to these two. So in this way we can understand that it is efficient fuel, but there is also some this is obviously advantage, but there are also some disadvantage. So now we will see what are the advantages and disadvantages both. Advantages of H2 as a fuel. First, see this. It is abundantly available in the combined state as water. It is true that in H2 state you may not get it, but in combined state there is amount hydrogen present. So if somehow from water you can prepare H2, obviously it can be a good source of food. Then uses of H2, the most important part. If you use H2 as fuel, it can provide pollution-free atmosphere because its combustion product is only water. So when it is undergoing combustion with O2, there is no carbon related, nothing related to carbon. So if you take any other fuel, just imagine the previous slide. We have methane, we have octane. So there is carbon, there are hydrocarbons. And when hydrocarbons are undergoing combustion, there is both formation of CO2 as well as formation of H2. But when you have taken H2 only, combustion product is only H2. There is no trace of carbon, right? So this is very important that when we are using it as fuel, the byproduct there is no problem. It is pollution free. Only pollutant you can get that will be oxide of nitrogen, because sometimes it may happen that due to presence of nitrogen as impurity in the hydrogen sample that you have taken, suppose if nitrogen is also present as impurity, that nitrogen in presence of oxygen, that is when you will do combustion reaction of H2, the N2 that is present as impurity, that also can react with O2 and it can produce oxides of nitrogen. That is the only pollutant possible, but that is not a very major issue. Now the disadvantages. H2 doesn't found in free state in nature. It is abundantly available as water, that is fine, but it is not available in free state, because if it is available in free state you can use it directly. But as it is not available in free state, you have to first synthesize it from water, then only you can use it as fuel, right? H2 has explosive flammability which causes problem to its storage and transportation. So when we are talking about fuel efficiency, obviously we have to store it, we have to transport it from one place to another, but that is problematic. The third point, a cylinder compressed of H2, it weighs about 35 as much as a tank of petrol, that is octane, containing the same amount of energy. Now suppose if you again look at this previous slide, if you fix the amount of energy, so it is, suppose it is 143 per gram. Now if you want to get if you fix these two values same, suppose you are making both of them 140 or both of them 40, then the mass that you will get for hydrogen for the same, to create the same amount of energy, to produce the same amount of energy, that is obviously high in case of that is H2. So compressed H2, it weighs about 30 times as much as a tank of petrol containing the same amount of energy. Okay, so this is the problem. Mass is high. Then H2 gas is converted into liquid state by cooling it to 20 Kelvin. So this is very low temperature, and this requires expensive insulated tanks. So you cannot just use any tank, it must be insulated. There should not be any thermal conduction property, because we are trying to keep it in liquid state, so the temperature must be low, and tank should be in which we are storing it, that should be insulated in nature, otherwise we cannot store it in the liquid form. Okay, so these are the disadvantage. Now to overcome this disadvantage, there are basically many methods that scientists they are trying to find. Now, one of these alternative for against this disadvantage is called hydrogen economy. Now, this is very modern term we use. So, what is hydrogen economy? From the term, you can understand that hydrogen economy relies basically on hydrogen, as if now it is the commercial fuel that will deliver substantial fraction of nation's total energy requirement and services, that is to burn hydrogen as a fuel in industry, as energy source or in power plants, and maybe also at homes and motor. Now the basic principle of hydrogen economy, we have to store it, we have to transport it in the form of dihydrogen instead of fossil fuel or electric power. So for other fuel sources, it is in the form of fossil fuel or electric power, but now if we want to use it as fuel, we have to do the storage, proper storage and transportation. Okay, but that is also a problem. That is a challenge actually, if that we have to face if we really want to make use of hydrogen as fuel, because it has some other advantages. There are two major barriers in achieving the goal of hydrogen economy. The first is to find out a cheap method for large-scale production of dry hydrogen, because it is not available in free nature. It is available in compound form H2O, but from H2O, if you want to make it in the preparation topic, we have seen it already that it is not very easier way to that production of dihydrogen in large scale. Because if we want to use it as fuel, obviously the scale requirement is there, but that is difficult. This is not a cheap method. So that is the barrier. And the second barrier is to find out an effective means of storing dihydrogen. So two barriers are there. One is preparation barrier, that is to make it is not very cheap method. And the second barrier is how to store it. Its storage is difficult. Okay, so you need insulated tank, that is, and those tanks, insulated tanks, they are also not very cheap. They are also expensive. It can be expected that economically viable and safe sources of dry hydrogen will be found in the coming years for its uses as a common source of energy. So we are hopeful for that. Probably someday we can overcome these barriers and use it properly as energy source, because it has some other advantages. Now related to this topic, that is hydrogen as a fuel. The correct statement among A to D regarding H2 as a fuel. It produces less pollutant than petrol. Now when you are talking about petrol, this is basically hydrocarbon. There is presence of carbon as well as hydrogen. Now when carbon and hydrogen you are doing combustion reaction, there will be formation of CO2, there will be formation of H2. H2 is fine, but problem is with CO2. So it is not pollutant free. But if you are using H2 as fuel, it produces less pollutants than petrol. It is true, because now you do not have any carbon. You simply have H2. So only H2 will be there, which we have just sometimes ago just read this information. Second is cylinder compressed dihydrogen waste 30 times more than a petrol tank, producing the same amount of energy. Remember, in the disadvantage part, this information is already there. So look at this part. So this information is also correct. Then dihydrogen is stored in tanks of metal alloys like Na, Ni5. So see here, metal alloys, that means two metals are involved here, sodium and nickel. So this is a special type of metal alloys are produced because this tank should be thermally insulated. Otherwise, we cannot store it in the liquid form. Then on combustion, values of energy released per gram of liquid H2 and LPG are 50 and 142 kilojoules. So it is saying that respectively. So when you are doing combustion, values of energy released per gram, remember the table where we have seen energy released per gram, per mole and per liter. Right? Now when it is per gram, then we have seen that liquid hydrogen and also gaseous hydrogen, in both actually. This is actually near about 140 to 143, and LPG, that is actually 50. But here it is mentioned 50 first, 142 second. That means as if 50 for liquid hydrogen and 142 for LPG. But that is actually not true. We can also check the table once more. So here you can see when you are considering per gram, for LPG it is 50, but for liquid dihydrogen it is 142. But here information is given in a reverse order, so this is not correct. So ABC only. All the statement correct, that is actually not present here. Fine. So see, this you can easily understand that this will be correct, because that already we have seen this information. Then B also we are sure. So if A and B, if we are sure about these two, so in the options A and B, both must be present. Now in which option you have both A and B present? It is only option 4. Because why I am saying so, because somehow this third statement you may not have previous idea that if the that is what this the material the tank is made of, what kind of material. Here it is saying that metal alloy sodium. So even if you do not know this, suppose C, you do not know whether it is true or false, but you know that A and B, these two are correct. So A and B must be present in the correct option, and A and B is together present only in option 4, but C is also present. Though the information of C, this is also very crucial information, that also I have mentioned in the table. So correct option is A, B and C. So this statement, even if you do not know, and that is not making any problem. Fine. So this chapter is basically complete with this hydrogen economy. As we have some time left, so one question we can discuss, though this question is not purely from this chapter, you can also say this question is from redox reaction, but as it is also involving H2O2, so we can discuss it here. It is asking that which of the following equation depicts the oxidizing nature of H2O2. We know that H2O2, it has reducing property, it also has oxidizing property. So we have to find in which case, this is single choice answer. Only one option will be correct. In which option it is acting as oxidizing agent. Now the easier way to answer this is just to find out that the other species with which H2O2 is reacting, is there any change in oxidation state? And if there is change, oxidation means the oxidation state will increase. So one by one we will check. The first equation, chlorine is involved with H2O. Now chlorine means it is 0, and chlorine is converted to HCl. That means from 0 to -1. So from 0 to -1, that means here H2O2, it has donated electron to chlorine. So this is basically reduction property. H2O2 is showing reduction property. Then the second equation, we have KiO4. Now IO4 ion, we have already seen it has oxidation state +7. Then it is reacting with H2O2. It is converted to KiO3. We have now IO3 ion, and this is +5. Now this is also reduction. From +7, we are getting +5. That means it has accepted 2 electron. With respect to iodine, it is reduction. So H2O2 is showing reduction property. Come to the third one. Here we have iodide, -1 charge over iodine. Acidic medium, that is okay. But what is the fate of I minus? Now it is converted to 0. So from -1 to 0, now it has lost electron with respect to iodine. So H2O2 is showing oxidizing properties. This must be correct. But why the last one? What is the problem here? See, it is simply reverse. Now iodine converted to I minus. So from 0 to -1, it is again H2O2 is feeding electron to iodine. So it is showing reduction property. Okay. So this is not oxidation, it is reduction. So here correct statement, correct equation, that is where it is showing oxidizing property. It is basically the third. So with this problem, we'll end this chapter here. So to next class, we'll start a new chapter. Fine. Thank you for listening. We are ending the session.